Hey guys, let's start. So I took a break. Now let's continue with where we left. And here we go. Let me check the stream. Everything good. So here, let's go in. Yeah. So pharmacology, non-cellular, cellular, molecular, pharmacodynamic, pharmacokinetic, insensitivity and hypersensitivity, antibacterial, fungal, cancerous, parasitic, nematodal, cestodal, trematodal, protozoal, okay, nematocide, ectoparasites, parasiticides, and properties of chemical drugs and their effects, and then the therapeutic and prophylactic purposes, medical pharmacology and veterinary pharmacology, which we know, natural and synthetic. It can be treatment, cure, or prevention, or control of physiological process. So example of control may be like insulin, that helps to injecting insulin as a drug, right? Like it helps to transport glucose to the liver and store it and reduce the blood glucose level. Yeah. Pharmacodynamics is the study of biochemical and physiological effects of drugs and their modes and actions. Okay. Effects and mechanism. Here in this case, like the mathematical numerical quantity of the drugs and concentration, and then the time, the extent of the drug exposure, and also it includes the liberation, absorption, and then distribution, and how it's excreted and how it is even metabolized and all those things. They are used for scope is to pharmacotherapy, treatment of diseases, and therapeutics, drugs, surgery, radiation, behavioral. Okay, so these are the areas there they use drugs. So what are the branches of pharmacology, which we already went through several times, like immuno, neuro, chrono, something to do with time, so biological timing, and then clinical, geriatric, psycho, cardiovascular, pediatric, gastrointestinal, respiratory. So these are the branches, and then the general one and specific one, and drugs acting on the central nervous system, cardiovascular system, autonomic nervous system, anti-inflammatory drugs, and chemotherapy of bacterial diseases. Okay. So name of the drug group, international names, generic names, substances, pharmacological effects, mechanism of action, pharmacokinetic, drug interactions, sections for use. So what are the things that generally you have to mention with specify with the drugs? Is like basically name, international names, pharmacological mechanism, pharmacokinetic, contraindications, adverse effects, drug interactions, instructions of use. Okay. Veterinary drugs, where are they used? For companion animals and farm animals. Yep, and we know that. And if the level of drugs is beyond certain limit, it will be also seen in the products produced by animals, like it can be in the meat, milk, and eggs. So what, there is a term to quantify it, like if it is beyond a certain limit of veterinary drugs, pharmacological drugs, you cannot consume that product. So that maximum allowed concentration of the residue in the food product obtained from an animal that has received a veterinary medicine has been exposed to a biocidal product for the use in animal husbandry. Okay, maximum residual limit. Okay, what is drug action? Drug receptor combination. Okay, how are they acting? Basically they combine with the receptors in the cell. So a best example is atropine, that is an antagonist for M cell receptors. So M receptors in the cells. Okay, so how do they affect the biochemical and physiological changes that occur in the consequences of the drug action? Okay, so one way is like what does it do? What does this drug, that when it combines with the M receptors, what does it do? It causes tachycardia, it causes reduced kidney and GI tract motility, and then reduced salivation, enzyme production, and so on and so forth. Yeah, lacrimation, bronchial secretion and stuff. Yeah. And then types of mechanism of drug action is like it can be outside the cell, like osmosis, and outside the cell it can be purely chemical, and then inside the cell is a section, and then on the surface membrane of the cell. Okay, so we will go through those things detail as we go down. So non-cellular mechanism of drug action is physical effects, chemical reactions. Okay, physical effects are protective, absorbent, lubricant properties, skin. Okay, so anything that is external. Okay, okay, chemically is basically in the one good example is here use of antacids that kind of neutralizes the hydrochloric acid in the stomach, produced in the stomach, kind of reducing the acidity. So what are those? Magnesium, aluminum hydroxide are examples. And moving on, non-cellular mechanisms of drug action, physicochemical mechanisms. A drug may alter the biophysical properties of specific fluids, surfactants, detergents, and anti-foaming agents. Okay. Physicochemical mechanisms. The drug may alter the biophysical properties of the... Okay. So anything that alters the biophysical properties, that has been termed under physicochemical mechanism. Okay. Like surfactants, detergent, and anti-foaming agents. Okay. And now another thing that is present outside non-cellular is like osmotic influence. Okay, right? So what it does is it impacts the electrolyte levels and fluid levels, and also alters the pH thereby by making it acidic or alkaline. And yeah. And we also went and googled what is diuresis, excessive amount of urination, basically loss of water electrolytes. So yeah. Okay, how do the cellular mechanism of drug action works now? So let's start with an example, because these things are quite similar, almost same, so it's very confusing. So let's go with an example. Here osmosis we heard, and then we also saw examples of detergent, anti-foaming agents. Here what are the examples? Inhalant anesthetics, they affect the lipid matrix, because the outside of the cell membrane is made of what? Phospholipid bilayer. So in this case it's made of lipid matrix. And then polymyxins are cationic surface active agents that disrupt membrane phospholipids of sensitive bacteria. Okay. The first one, inhalant anesthetics affects the lipid matrix, and polymyxins affect the phospholipid layer of sensitive bacteria, certain bacteria which are sensitive to polymyxins. Okay, so the next one is okay, and then now we are going to see cellular mechanism, in this case the cell membrane part of it. Okay, how it affects the cell membrane. So let's just highlight this one, cell membrane. Yeah, so how does it do? The local anesthetics affects the sodium channels in excitable membranes, wherever the excitable parts are there. So it prevents depolarization. That means it prevents the cell from getting to an excited state at all. So let's say it's a muscle cell, it will never can start contracting, in this case. So next one is calcium channel blockers that inhibit the entry of calcium into cells. Okay. And then insulin facilitates the transportation of glucose into cells. Okay. Calcium blockers, sodium inhibitors. Calcium also, once again, nerve impulse conduction. That means you cannot do a lot of maybe motor functions, you might get paralysis and stuff. So there are blockers as well, calcium channel blockers as well. And then between one axon and the second axon, or sorry, between a neuron and another neuron, there won't be transfer of electrical impulses if the calcium blockers are there. So insulin facilitates transportation of glucose into cells. Yep, obviously, right, into the liver cells, right? That's the main function. Best case is example of diabetes patients. They sometimes have to orally take insulin or through injections. So yeah, trying to reduce the blood glucose level. So inhibition may be competitive or non-competitive or reversible or irreversible. So what kind of inhibition? Enzyme inhibition. So it happens here extracellular. It happens on the cellular level on the surface membrane, right? So examples. Let's go with an example. Enalapril. It's like enal and april. Enalapril. Okay, so what does it do? It decreases blood pressure. We'll see down below how it does it do. Decreases blood pressure by inhibiting the angiostensin converting enzyme. And then pymobendin is an inhibitor of phosphodiesterase type 3 isoenzyme. So positive ionotropic and vasodilatory effect. Okay, positive ionotropic increases positive ionotropic and vasodilator effect. So one reduces the blood pressure, the another one is positive ionotropic and dilates the blood vessel. Okay, so in this case, yes, angiostensin converting enzyme. So kidneys produces an enzyme called renin. Okay, that is very essential for reducing the blood pressure and then they're producing the blood volume thereby, and then overall blood pressure in the body reduces. So what renin does is it triggers angiostensinogen to become activated angiostensin 1, and then angiostensin 1 cannot become angiostensin 2 without that angiostensin converting enzyme, which is where the ACE inhibitors come into play, and then they block it. So thereby you are reducing the blood pressure. When you inhibit this conversion from 1 to 2, the blood pressure falls. Okay, cellular mechanisms of drug action. Okay, acetazolamide. Okay, let's just mark this. Acetazolamide is an inhibitor of carbonic anhydrase. Inhibitor of carbonic anhydrase. What does it do? Diuresis. It is used as a treatment for diuresis, I guess. So meloxicam is anti-inflammatory, antipyretic, analgesic, which is pain blocker. So what does it do? It inhibits the COX-2. And valproic acid, basically it inhibits gamma aminobutyric acid, I guess. Yeah, gamma aminobutyric acid. So inhibitor of gamma aminobutyric acid transaminase. So this enzyme it kind of inhibits. So what happens because of that? Anticonvulsant effect. What is anticonvulsant effect? Certain medications to prevent or reduce the occurrence of severity of epileptic seizures. So to prevent epilepsy, we can kind of use this valproic acid. Okay. So the epileptic twitches, those things can be removed. And then fluoroquinones, bactericidal effect. That means it kills bacteria by inhibiting bacterial DNA gyrase. Okay. Thiampenicol. How would you say thiampenicol? Okay. This is bacteriostatic effect. What is bacteriostatic means? How is it different from bactericidal? Basically, static means it holds something, like instead of killing a cell, it prevents a cell from multiplying. Basically, that's how it kind of inhibits the control or inhibits the growth of the bacteria. And then what happens is the human immune system gets triggered and the immune system kills the bacteria and thereby producing immunity naturally. So that's a cool stuff. Now moving on to the okay, what is this mechanism of action of NSAIDs? Okay, COX-2. We know COX-2. What is COX-2? Which one inhibits COX-2? Not the valproic acid, not the first one. Meloxicam, I think. Yeah, meloxicam. Yep. So COX-2 inhibitors, prostaglandins, mediate pain, inflammation, fever. Okay, one of the examples of meloxicam based drugs is like ibuprofen, aspirin, those things. Yeah, and then they're all derived from arachidonic acid. So that's something it's good to know, I guess. Arachidonic acid produces prostaglandins, or it converts to prostaglandins and then causes all these things. And then prostaglandins here, production of gastric mucosa. Okay, COX-1, production of gastric mucosa, and hemostasis. Okay. Okay. We know homeostasis. Do we know hemostasis? Something to do with blood? Okay, this is how blood clot happens. Okay. Okay. Excessive blood loss, prevents excessive blood loss, hemostasis. Okay. So COX-1, both the prostaglandins are produced in the hypothalamus of the brain. Okay, arachidonic acid becomes third. What is NSAIDs? Or non-steroidal anti-inflammatory drugs. So what does it mean? Non-steroidal means it's not intracellular, it's basically on the surface of the cell membrane, basically surface of the cell. So non-steroidal anti-inflammatory. Yeah, obviously. Reduce inflammation, pain and fever. Yeah. So now the same cellular mediated mechanism of drug action, receptor mediated effects. Okay, how the receptor locks with the ligand or any drug molecule, and then how it acts. Many drugs interact with the specific proteins known as receptors. Yep, present on the cell surface. As a result of interaction, activation and inhibition of sequence of biochemical events is usually initiated. It can be activation or inhibition. Okay, receptors may be located on the cell membrane for sure, and in the cytosol or in the nucleus as well. So there are also receptors present inside the cell as well. Okay, the best example of toll-like receptor, nod-like receptors. So some of the toll-like receptors are present outside the cell membrane, along the cell membrane of a bacteria, and then some of them are located inside the nucleus and stuff. Actually not the bacteria, my bad, it's basically the macrophages or any of the WBCs. Okay, so those cells kind of recognize pathogens. Okay, how they recognize pathogens? Because of the presence of toll-like receptors on the surface of the cell and maybe also inside. These toll-like receptor detects the double-stranded DNA, double-stranded RNA, and then the flagella trying to detect gram-positive negative bacteria, lipopolysaccharide layer of bacteria, and then once they detect something, and then they trigger the immune response, right? Yeah, by producing cytokines. So there's a close correlation between drug structure and then drug activity. Yep. So now probably they're going into the structure part, I guess, trying to explain the structure, receptor types, and then G protein coupled receptors. Okay, this is a nice one which I remember from previous semesters. Receptor type, receptor mediated effects. agonist, antagonist. It's all right. Let's go. Let me check the stream. Everything is okay. Nice. So they are talking about transmitters, substances that are chemical substances that are released by the nerve terminals, which diffuse across the synaptic cleft and bind to the receptors. Basically, they have shown it here. So they produce transmitters from this terminal of the neuron, and then these transmitters come and attach to the receptors. These are the receptors actually. They attach the synaptic cleft. Once they attach it, they trigger some kind of a response here. Yeah, here you can see here also. See, these ligands come and attach here. So these pink dots or circles are basically neurotransmitters. That's what they are trying to say here. Noradrenaline, adrenaline, acetylcholine, GABA and stuff. So we can see what are their functions, what do they do. Okay. Noradrenaline, alpha 1 adrenoreceptors, beta 1. Okay. So what does noradrenaline do? Vasoconstriction in skin and viscera. Okay, vasoconstriction. Okay, what is adrenaline causes? We kind of can guess what does adrenaline do. It increases the heart rate, it increases the like the fight or flight response, right? Like you start your basal metabolic rate is increased and stuff, right? So yeah, you can see here increased heart rate, bronchial dilation, like breathing heavily and stuff. What does acetylcholine do? Basically helps in the muscle contraction or like motor action activities and stuff, and other things as well. So gastrointestinal smooth muscle contraction, acetylcholine. And glandular secretion as well. And then once again, M and N receptors of acetylcholine are there. Here beta 1, beta 2 adrenals. Skeletal muscle. Okay, it's skeletal actually. Yeah, skeletal muscle contraction. Okay. So moving on. So you can see here sodium channels are there and then calcium channels are there. So this is where the drugs also act, and they block the sodium channel, block the calcium channel. If these things are blocked, the neurotransmitters will never be released. So because of that, they can have some kind of a reaction based on that. It can be anything. In this case, it could be like you cannot contract your muscles anymore, you don't have any voluntary control of your motor actions. So this entire image is basically trying to show how it happens actually. So here acetylcholine, we know, right, how acetylcholine is formed. Choline and then acetyl-CoA, these two combine to form acetylcholine, and they are stored inside vesicles. These vesicles come to the surface and release the acetylcholine actually, and then they attach to the ligand. Okay. The four main types of receptors: ligand gated, okay, which we just saw now. Yeah, GABA, NMDA. G protein coupled receptors, that's also an important thing, where like certain ligands come and attach the cell surface, and G proteins that are present in the near the receptors gets activated. Yeah, so what do they produce? Examples: dopamine, histamine, all the acetylcholine, neurotransmitters, and then yeah. Okay, ligand gated, G protein coupled. Okay. They have not explained what are the other two, I guess. I guess this is the other two. Nuclear receptors, and then tyrosine kinase associated receptors. Tyrosine kinase associated. Okay, let's go through the G protein coupled receptors here. G protein coupled receptors are linked to physiological responses by second messengers. Okay, yup. They act as a second messenger basically, because whenever ligand comes and attaches to the cell surface, the G protein that are released inside the cell acts as a second messenger actually. See, the second messenger are chemicals whose intracellular concentration increases or decreases based on the response to the activation by a transmitter substance, noradrenaline or adrenaline, on the surface of the cell. So what are the second messengers actually? In this case, cyclic AMP, cyclic GMP, diacyl glycerol, okay, calcium ions as well. Yep. Nice. Okay, so cyclic AMP, GMP, calcium ions, diacyl glycerol. Okay, so what they are trying to say is, what these are the receptors where the ligand comes and attaches the adrenaline or noradrenaline or whatever the thing, dopamine or whatever it is, it comes and attaches here. When it attaches, what are the secondary G protein messengers that are going to get increased? So these three receptors is going to increase the cyclic AMP. There are two receptors that decrease the cyclic AMP, which are dopamine, D2 dopamine, and then alpha 2 adrenoreceptors. D1 and beta 1 adrenoreceptors increase cyclic AMP, alpha 2 and D2 reduces the cyclic AMP concentration inside the cell. So angiostensin receptor reduces cyclic GMP, and then histamine receptors increases DAG. So ligand gated ion channels. Okay. They are explaining the image of a ligand gated channel where GABA, this is where the GABA binds. synaptic vesicles having norepinephrine here, and then this is where what is present, alpha 2 adrenoreceptors, and here alpha 1 adrenoreceptor is there, presynaptic membrane, postsynaptic membrane, and synaptic cleft, the space. Okay. And then the receptor type is nuclear receptors. The third and fourth type of receptors are there. And the androgen receptors, what are the third and fourth type? Androgen receptors, glucocorticoid, androgen, glucocorticoid, estrogen and progesterone receptors, thyroid hormone receptors, vitamin D receptors. So okay, well, let's try to recollect and remember what is happening. Nuclear receptors are present on the cell nucleus and regulate transcription, thus protein synthesis. Okay, nuclear receptors are present on the cell nucleus, so it's intracellular already. And then what they do, they regulate transcription and thus protein synthesis. So what are the receptors that are present? Vitamin D, thyroid, estrogen, progesterone, glucocorticoids, androgen. And then tyrosine kinase associated receptors as well. Kinase associated receptors are insulin receptor, tyrosine kinase associated receptors, insulin receptors. Okay, let's remember that there are 4 types. The first one is ligand gated, and then the next one is what? Ligand G protein. Okay, G protein coupled receptors, and then nuclear receptors, and then tyrosine kinase associated receptors. Okay. Drugs may act like a agonist or antagonist. Okay. Okay, so antagonists can also be known as blockers, and agonist is the one that activates basically. Maybe we can write some text. Activators here, blockers. Can we increase the font size, please? Blockers. Okay, and yeah, that's enough, I guess. Okay, drugs has 2 roles. One is affinity towards the receptors, and then what else it does? Intrinsic activity. Affinity is the one that causes it to bind to a receptor. Yeah, intrinsic activity is where property of the drug that permits the initiation of post receptor processes that can lead to a response. It can be either muscle contraction or muscle contraction inhibition, It can be anything. Enzyme secretion or enzyme secretion inhibition, or protein synthesis inhibition. Depends on its antagonistic or agonistic nature. Uh, Agonist is a drug that has both affinity and intrinsic activity, combines with the receptor and initiate the sequence of events that leads to, okay, the examples. Now once again the examples, okay. Let's go with something that we know, morphine. So morphine is a agonist of opioid receptors. Okay, it goes to opioid receptors, and agonist means it activates it, it does something because as analgesia. Though it leads to fainting, I guess, yeah. And I don't know any of those things, but still let's go through it, run through. So carbachol is an agonist, okay, of M receptors. Before we read, you remember atropine, right? Reduces blood pressure, I think so. Yeah, carbachol is an agonist of M, increased gastrointestinal motility. Okay. Carbohydrate or something, it's like kind of easy to remember. So carbachol increases gastrointestinal motility and glandular secretion. Salbutamol is an agonist of beta 2 adrenoreceptor. Bronchodilation. Salbutamol, bronchodilation. Xylazine causes sedation, analgesia, and muscle relaxation. Xylazine. Alpha 2 adrenoreceptor. Now this is agonist, and now examples of antagonist, and then some more stuff, and it's almost done, guys. We are there. We are reading all this for the first time. It's okay, not bad. Yup. So it has an affinity, of course, to attach to your receptors, but it lacks that intrinsic activity. Okay, so that's the important part of antagonist. So let's go for the examples first, or we can antagonist interacts with the receptor to inhibit. Yeah, inhibit what? The agonist, the ones that wants to activate something or to create some intrinsic activity. So atropine, propranolol, haloperidol, cimetidine. Wow. When you say these names for the first time, it's so funny. You feel like you just forgot English, Atropine is an antagonist, yeah, of muscarinic M receptors. What does it do? It's an antagonist, right? So something it inhibits, okay? So inhibition of gastric and salivary gland secretion, dilation of smooth muscle in the GI system. So it causes dilation, okay. And bradycardia. What is bradycardia? The heart rate is abnormally reduced. So that's the thing. It causes bradycardia, it causes dilation of the smooth muscles in the GI tract, it inhibits the gastric and salivary secretion. Haloperidol is an antagonist, okay. Oh, once again, it causes sedation. It stays in the receptors of central nervous system, causes sedation, antiemetic effect, and hypotension. And propranolol is an antagonist of beta 1 beta 2 adrenoreceptors, causes bradycardia, antiarrhythmic Arrhythmia, anti-arrhythmia. Okay, arrhythmia is some kind of an abnormal heart rate, heart beating. So anti-arrhythmia. Okay. Hypotension and broncho. Hypo means something reduced. Tension means somewhere tension is reduced. Hypotension, maybe blood pressure reduction, I guess, or muscular hypotension. So yeah, bronchoconstriction. Okay. And then it's an antagonist of H2 receptor, inhibition of gastric acid production. Inhibition of gastric acid production. Let me check the stream if everything is good. Wow, one more 40 minutes. So let's go over one more time. So atropine, muscarinic chemoreceptors causes most of them. Let's see what are the things they cause. They cause bradycardia, hypotension. They cause inhibition of gastric and salivary gland secretion. Enzymes prevent the enzyme secretion. Okay. Dilation of smooth muscles, bronchoconstriction. So something always constrict. None of them are relaxing other than the smooth muscles. And then inhibition of gastric acid here. Okay. So here increased gastrointestinal motility and glandular secretion. Increased secretion, there decreased secretion. Okay. Carbachol, there atropine. Morphine causes analgesia, but what does it do? It agonistically affects the opioid receptors. Okay. And xylazine alpha 2 adrenoreceptors cause sedation, analgesia, muscle relaxation. Here all muscle relaxation. Here bronchoconstriction and hypotension. And then yeah, let's see what is antiarrhythmic and antiemetic. Check the stream. Antiarrhythmic, antiemetic, and then maybe we can also put hypotension. Okay, what does it do? Hypotensive lowers blood pressure, arrhythmic lowers heart rate, right? So basically it kind of reduces the blood pressure. Antiemetic means prevents the relieves nausea and vomiting. Okay, antiemetic prevents nausea. Okay, got it. Haloperidol, sedation and prevents nausea. Okay, let's see. Antagonist may act in a competitive or a non-competitive and then reversible or irreversible manner. So that's something which the enzymes and the substrate how the enzyme and receptors activate. In this case, the enzymes are the drugs that activate with the receptors of the cell, either competitively, non-competitively, reversibly or irreversibly. The effects of competitive antagonists can be overcome by increasing the dose of agonist. Okay, how can you overcome a competitive antagonist? By increasing the dose. Okay, thus antagonist is acting reversibly at the receptor site. Thus you are reversing the effects, right? So if it is a non-competitive antagonist, it's really hard to overcome. Even if you increase the dose, nothing is going to happen. So it cannot be controlled, okay? Because irreversible binding of antagonists at the receptor prevents initiation of the effect. Yeah. because they irreversibly attach it, and like once and for all, if they attach it, they will never leave. So that's how it is. So we cannot do much. So yeah, non-competitive irreversible antagonist is really hard to control. If it's a competitive one, we can just increase the dose of agonist. Okay, let's go. We are almost there. Almost there. So agonist, antagonist of receptor, endogenous ligand, receptor, effect. So the ligand attaches. This is, can be the drug here, and then agonist, antagonist. No effects, right? So when this thing comes and attaches, it prevents any kind of agonist to join here. So basically, yep, got it. Here agonist causes the effect. Okay. Here ligand attaches also, it causes the effect. The drug agonist also kind of supports it in a way. It has an active site of similar shape to the endogenous ligand, so binds to the receptor and produces the same effect. Yeah, it takes up this receptor space and so prevents the endogenous ligand from binding. So what in this case is the agonist kind of takes the shape of the receptor of the endogenous ligand. So basically the ligand still comes and attaches, and then it does its job. Whatever the ligand triggers, it will trigger. So yeah. So what does this image say? Receptor, antagonist, nothing. Oh, so it's agonist, right? Sorry, agonist, and then against receptor complex, and then pharmacological response. If antagonist comes, there's no agonist that can see, no pharmacological effect. Okay, there should be a safety. Yeah, the first of all, the drug level should be enough to cause a significant effect, and also it should be a safer dose. That's what they're saying. Therapeutic index is a measure of the drug safety, is equal to LD50 and ED50. What is LD50, ED50? It's written here. The higher the value, the safer the drug. Okay, very nice to know. So now let's see what is LD50. LD50 is the dose of the drug that kills 50% of the exposed population. ED50 is effective dose. Is a dose of the drug that produces an effect in 50% of a population. So LD50 basically guarantees to kill 50% of the exposed population. Here it will at least have some effect on the 50% of the population. Okay. ED and LD50. Okay. That ratio. Okay. So that's it, guys. Thanks for putting up with me. So we did it 50 minutes, 2 sessions we did it. So thanks, guys. See ya.